Hello again. How about we check out what's going on in section 3.2, polynomial functions and their graphs. So recall from section 3.1, we looked at quadratic functions, which was just a special case of a polynomial function. Now we're going to expand that to include higher degrees, and as we include a higher degree, we're going to see more hills and valleys. So here's what we're going to work with. Transformations to sketch some polynomial functions. We'll use this leading coefficient test to determine the end behavior of our polynomial functions with respect to their graphs. We'll find zeros, and remember a zero is just another name for an x-intercept. Then we're going to use a theorem to help us locate where those zeros are for our polynomial function. So it's important for someone who studies data and looks at trends, it's important that that person be familiar with all the different types of equations and the graphs that they produce. That's important to effectively model a real-life situation into an equation. And so a polynomial function is just another one of those tools we have to maybe model real-world scenarios. So remember, we saw this definition of a polynomial function earlier in section 3.1, and it's just the general format that a polynomial function can take. This guy at the end is just the quadratic. But now we're going to extend our work to higher degrees, higher than the square, which is our quadratic. Keep in mind that in the degrees must be a non-negative integer. So we can't have negative degrees. And these a sub n's are just our coefficients. So let's take a look at an example of a higher degree polynomial. Let's suppose we have this one. And remember, a polynomial is in standard form if it is in descending powers. So if you're given a polynomial and it's not in descending powers, you need to write it that way so you can determine the degree of your polynomial. So look, I've got fifth, fourth, third, second, first, and a constant. So those degrees are in descending powers. The values in front of our variables are our coefficients. This guy at the end is our constant term, and this guy up front is our leading term. And that leading term will always tell you what the degree of your polynomial is going to be. So in this case, we have a fifth degree polynomial function, or polynomial. It's not a function yet. It would be a function if we did this. And actually, we're going to do that in a little bit. But we're just considering the polynomial here. Okay, so first thing is, which of these equations or these functions below represent polynomial functions? So we got to look at the degrees, and this one has a degree of 1, so it is a polynomial function. Nothing else, nothing weird going on. Why would this next one not be a polynomial function? Well, because we have a division of sorts. He is not a polynomial function. Next guy is a quadratic. He is a polynomial. Number 4, what makes this guy not a polynomial function? If you guess the 1/2, then you guessed correctly, because our degrees have to be non-negative integers, and 1/2 is not an integer. Finally, this last guy is a polynomial function. All our exponents are positive integers. We're in descending powers. We are good. So when we graph these polynomial functions, we're going to get some really cool curves that's going to always be smooth and continuous. Okay, I can't spell. All right, so we may see this W shape. Remember, we saw parabolas. We may see several hills and valleys. Noticing the end behavior, in this case, both ends go up. In this case, both ends are going up. Here, the left is going down, the right is going up. Left is going up, right is going down. So we're going to see a theorem that's going to help us determine how those ends behave. Well, the simplest polynomial to graph is a monomial, because all we have to do is use our rules for shifting and reflecting to graph those. They're not going to have a bunch of hills and valleys in between them. So let's consider some monomials. They're often referred to as a power function. So basically, it's just an x to the nth power that's either moved up, down, left, or right. What we're going to notice is if that degree on n is an even number, like x squared, x to the fourth, x to the sixth, it's going to behave exactly like x squared, except here at the origin, it's going to be a little bit flatter and it's going to rise a lot faster, but that's still that basic parabola shape. If that degree happens to be odd, like x to the third, fifth, x to the seventh power, it's going to have the classic x cubed shape, but as the degree gets higher, what you're going to see is it flattens at the origin and is going to rise a lot faster than the basic x cubed shape did. All right, so let's just sketch these transformations of our monomials. So I'm going to look at my degree, and it's 5. So in my head, I know the shape of that because it looks just like x cubed. So I have x cubed in my mind because it's odd. Because there's a negative in front, it means we need to flip x cubed across the x-axis. Remember that negative in front means to reflect. So the basic shape of a negative x to the fifth would look like x cubed, flatter at the origin, but flipped over, which means we would have something more like this. Ooh, that wasn't great. Yeah, these aren't the easiest ones to graph. Let's see if I can do a better job with that. A little flatter there and then going out. Okay, so there's a negative x to the fifth. Let's take a look at this one. When it is an even degree, we know it's going to be a parabola shape, but it's going to be flatter here around the origin. So x to the fourth looks just like x squared, with a few exceptions, but the same basic shape. Now, recalling our transformations, this one is going to move where? It's going to move left 1 unit. So it's going to be this x to the fourth shape, but I'm just going to shift it left 1 unit. Now you certainly could do these on your calculator, but it takes more time to plug that in the calculator than it does just to recognize, well, what's happening here? Okay, so when you have a polynomial, you want to write them in descending powers. So here's a situation where we're going to write the negative x cubed first and the constant second. Well, we know what x cubed looks like. We wrote it just a second ago, but it looks like that. Now the negative in front of him says I'm going to have to flip him over, so he's going to do something like this. And the plus 7 means he's going to go up 7. So let's graph that guy. So the x cubed flipped over up 7. So here is 7. Let's assume 1, 2, 3, 4, 5, 6, 7. And it's the flipped over version, so it's going to look like this. Put in your calculator, you'll see that's the shape you get. So sketching monomials is not that bad. When we start putting more x squares, x cubes, x to the fourths in between, that's when we get a lot more hills and valleys. So I would like to be able to determine maybe how the ends of my polynomial are going to behave. Let's just say when I look at my polynomial, how will the ends behave? Will they both go up? Will they both go down? Will one go up and one go down? and it's really easy to figure out. The way we're going to figure out our end behavior is by looking at the leading term. And we're going to look at the coefficient on that leading term, and we're going to look at the degree. If you know what x squared and x cubed looks like, then you can determine the end behavior of any degree polynomial function by just looking at the leading term. Okay, I know this is a lot of information here in this blue box, but before I look in the blue box, let's just think. You can do this. If your degree is even, what did I just say a second ago? They're going to all look like what? A parabola. So if that degree is even, then either both ends will go up or both ends will go down, because the ends are going to behave like a parabola, whether that's a 6th degree or a 102nd degree. The ends will behave like a parabola, both up or both down. Now, what is it that tells you whether a parabola opens up or opens down? The number in front. So if the number in front, if that a sub n is negative, both ends are going to open down because it's a flipped over parabola. If the front number is positive, then both ends will go up, like a regular opening parabola. That's something we covered back in chapter 2, and it's good to remember those rules because they come back in to haunt us, actually. So if the degree is even and the front number is positive, both ends go up. If the degree is even and that front number is negative, then both ends are going to go down. So what do you think is going to happen if the degree is odd? That means, in your leading coefficient, that degree might be 5 or 7 or 9. The ends are going to behave like, what do you think? X cubed, of course. So if the degree is odd, your ends will either act like x cubed, where the right side goes up and the left side goes down, or the flipped over version, where the left side goes up and the right side goes down. So if the degree is odd, you'll have one of these two scenarios. How will I know which scenario it's going to be? Depends on that leading coefficient. So if a sub n is positive, then it's going to act like x cubed, where the left went down, the right went up. And if a sub n is negative, then it's going to be a flipped over x cubed, which means the left goes up and the right goes down. But you know what? If you forget, you can just use your calculator to help you remember how those ends behave. So if you understand what I just mentioned right here, dealing with even or odd, then you understand everything in that blue box. So I am not going to go through the blue box. Let's use the leading coefficient test. So first thing we're going to do is make sure our polynomial is in descending powers. 5th, 2nd, 1st, yes. 4th and 2nd, yes. 3, 2, 1, yes. They're all in descending powers. So I'm going to next look at my leading coefficient. I don't know what's going to happen in between my ends, but because the leading coefficient has an odd degree and a sub n is positive, it acts just like x cubed, where the left side goes down and the right side goes up. Or we could say it falls on the left and rises on the right. Okay, leading coefficient, leading term here. Aha, it's a 4th degree, so I have an even degree. That means the n's are going to behave like x squared. The front number a sub n is negative. So will that parabola be opening up or opening down? Opening down, so what we'll see is that both ends go down. Or you could say they both fall. Last one we have is this guy. It is an odd degree. 3 is odd. So the degree of this guy is odd. And the front number, a sub n, the coefficient in front of that is negative. So odd degrees all behave like, excuse me, x cubed. Now I'm going to have to take that x cubed, since the front number is negative, and flip it over. So instead of the left going down and the right going up, the left will go up and the right will go down. But if you don't remember, you know what you can do? Just type negative x cubed in your calculator. And whatever happens with those ends is how the ends of this polynomial will behave. You could just type in your calculator negative 5x to the 4th. That's going to tell you how your ends behave. Or you could type in your calculator x to the 5th if you've forgotten. Well, I'll stop this video here and pick up the next video with the remaining information. Let me know if you've gotten questions.